Good afternoon, student. In today's class, we are going to discuss about the two concepts. First concept is state diagrams. Second concept is registers and counters. So before proceeding with the next concepts, let us consider what's the meaning of state diagram. How do we design the state diagram? Okay, so basically states are nothing but the binary inputs of zeros and ones when we are combining with different bits. Like we had BCD code is there, we had hexadecimal code is there, we will be having 7-segment code is there. There are different codes, right? So as we have seen those number of codes in combinational circuitry, when we want to design certain number of codes, when we want to find out the combination of those codes, so to do that particular codes into a particular format, we are going to design the state diagrams. State diagram, to do the state diagram, we should have the 4 steps. First step is that we should know the circuit diagram. Okay, that's the step 1. After knowing the circuit diagram, next we need to write the equations, state equations. After drawing the circuit diagram and state equations, we have to make a tabular, that is state table. After knowing the state table, then we can draw the state diagram. So these are the steps we need to follow whenever we are going to design a state diagram. So step 1 is for circuitry, step 2 is for equation, step 3 is for state table, and step 4 is for state diagram. So these are the steps to reach out for state diagrams. So basically state diagrams tell us about how the flip-flops or the combinational circuitry or sequential circuitry can be drawn in a graphical form or a pictorial form. Like when you want to write a sequence of data, when you want to write that particular data, what is the output end? For example, if I want to go for basic gate, if I want to write, suppose I am writing an example of AND gate, right? What an AND gate consists of? It consists of 2 inputs, A, B. So if I want to multiply it is A into B, right? So what I did first thing, I draw the circuit diagram. So I know the equation. So that is equation is what? A into B. That is the second one. This is step 1, step 2. Next is tabular form of it. So AB, it's 0, 0, 0, 1, 1, 0 and 1, 1. So output of it would be 0, 0, last is 1. AND gate will be multiplied, right? After knowing these things, I need to write the states. So in the states, it is a pictorial graphical representation. So first state is what? What is the input of first state? 0, 0, right? So what is the output over there? Output is still 0. So here we'll write the output. Next, second stage is what? What is the output value? Next stage input combination 0, 1. Next input combination, what is the output value for it? It is again 0, right? Next, what is the next input combination? What is the next state? 1, 0. What is the output for it? It is 0. Likewise, what is the next state we do have? 1, 1. It's 1, 1. What is the output for it? We'll write an arrow mark upper side and we'll write the output followed by input. But since we are writing the state, so I have wrote 1. Likewise, I'll stop the end. This is what circular way I'm just representing the basic example. How do we design a circuit diagram for given basic gates? So this is just an example, student. So based on that, we need to draw this circuitry symbol. How do we take that circuitry symbol whenever we want to design this state diagram for any kind of flip-flops or registers or counters? Okay, so our next topic for our discussion would be the registers and flip-flops. So before proceeding with that topic, so what we have discussed in the state diagram is that to do any kind of state diagram, we should have the circuitry diagram or circuit symbols, whatever the circuitry we do have, we need to draw first circuitry. After that, we should know the equation for it. Then we need to make a state table. In state table, if you want to design a flip-flops, you will get 2 states. One is the next stage, then the present state. So we do have to consider both the state. Then whenever we want to write these diagrams, in that we will have to write a output followed by input. So this we don't have for the 2 states. That's the reason I have write inputs as a states only. But when we want to go for flip-flop designing or any other kind of designing, in that we have to consider the states separately. Then in this arrow marks, what all the numbers I have written over here, these are called output followed by input points. We'll write on the upper side of the arrow. So this is the way we can write state diagram. So here we end it. So I want to make it cyclic form, so I have made one more circle in that way. So this is the way state diagram can be designed for any given kind of conditions, or for the gates, for the flip-flops, for your completely combinational circuit or sequential circuit. Asynchronous or synchronous. Synchronous we have seen, that is what Mealy and More machine. Asynchronous we are going to learn in today's class, that is registers and counters, how it is going to be useful for designing the registers and counters. The second concept for us to discuss would be the registers and counters. So what's the meaning of registers? So register is a flip-flops. It's a combination of flip-flop. It is going to store a bit of information. So register is also a combination of flip-flops. So to design the registers, what we are considering? We are considering the flip-flops. So by considering the flip-flops, we can design the registers, and it is going to store a bit of information. So it is going to store a bit of information in the form of what? By using the flip-flops, right? Zeros or ones, in the form of zeros and ones. Next, if you do have n clock pulses, or if you want to store n bits, we have to use the n number of flip-flops. Okay, so these are the definition for registers. So registers are the basic blocks in the sequential circuitry, which is going to take a group of flip-flops. Each of that can be shared a common clock pulses, and it is capable of storing a bit of information, in which if you are using n flip-flops, it can store the n bits. Clear? So that is called registers. And the registers is also used for making the operation of your binary gates. Meaning is that when you want to perform any kind of binary information, what we call this storage of it, that can be done by using the registers. Clear? Next is the counter. So as the name itself, it's a counting. It's going to count the number of states. The counter is also capable of storing a data, but here the main important point is it is essentially a register that goes through a predetermined sequence in a binary states. So what we are saying, we have to use here the words we are saying counter. Counter is also a group of registers. So group of registers we used, and we'll try to count the sequence which we are having predetermined. It is going to take a predetermined sequence. It is going to count that particular sequence. Okay, for that purpose we are going with counters. So in the counters, the most important point what you need to remember is that it is going to have a predetermined sequence in a binary states that can be used the gates and connected in such a way that it can going to provide the sequence. Okay, so that is how the counter is going to be used. So let us see one example of one flip-flop. As I am saying, it is using what? Group of registers. Register is consist of group of flip-flops, right? So I'll take one example. How the group of flip-flops or group of registers is going to be taken. One D flip-flop will take it, and we'll try to use how it is going to be used for storage purpose. Now take an example of 4-bit data register, student. So we are taking 4-bit data register. Okay. So by using D flip-flop, I want to design the 4-bit data register. So what's the meaning of 4-bit? It should have the 4 inputs that I'm defining as I0, I1, I2, I3. These are my inputs. And I'm saying the output for that 4 bits are A0, A1, A2, A3 and A4. So I'm using D flip-flop because registers can be designed by taking the groups of flip-flops. So if I want to take it D flip-flop, So what D consists of? It consists of 4 Ds. So we have to use 4 types of Ds in a sequence form, right? So this is what? First D, second D flip-flop, next D and next D. Each should have a clock pulse, right? So all are passing to one common clock pulse. This is a clock pulse, right? So these are what actually? These are the inputs. What are the inputs we are giving? What is the first input we had? I0, next input is I1, next input is I2, next input we do have is I3, right? So these are our inputs value. What about the output? We are saying for each flip-flop output is A0, A1, A2 and A3. So this is what? This is our clock pulse. So I will write mention here, it is a clock pulse. Okay, clock we are giving. Now we need to give a reset also, so that whenever it is going to be terminated, it is going to get the reset also. So what we are saying, this is what? Reset end. Reset, this is clock. Clock 0, clock 1, reset 0, reset 1. So clock, reset, reset. No need of mentioning 1 to 3. It's a common, right? So we are not segregating separately. We are giving common. So reset for all. This is the reset connections. So this is what? Reset bit. So this is what actually? This is a 4-bit data registers. By using 4 bits of data, if you are using by using D flip-flop, this is our output, right? Q. It can have also Q bar, because D flip-flop have one is a Q, another is a Q bar. But only I am mentioning one flip-flop. So how do we design? We have taken 4 types of D flip-flops. By considering the 4 types, what we have considered? We have considered their particular inputs by taking the different values. So as I mentioned here, I0, I1, I2, I3. If you want to get 4-bit data, 4-bit means what? How many combinations? It's 2 power 4. That is 16. 16s vary from 0 to 15. So these number of bits, it is going to be count by using this particular 4-bit data register counter. Data registered. Now we did not reach out to the counter. So to get this thing, this is the way we'll design. If they say T flip-flop, instead of D you can mention T. If they give JK, you have to write J and K, J0, K0, J1, K1, J2, K2, J3, K3, right? So this is the way we can design the given flip-flops into their respective value, where it consists of clear bit, that is reset, or you can mention that particular thing is clear. So as I'm saying clock over there, so I'll mention here it is clear. So clear, or you can say reset also, that is the meaning is the same thing. Then so the main purpose of these kind of flip-flops is going to get the simple form of 4-bit data. And in this, most important thing would be, how do we get the clock pulse? If you're using positive edge of the clock pulse, and if you're giving reset of it, whatever the data you want to get from it, it's going to monitor, it is going to provide that particular bit of data. Clear? So this is the way we'll write one data. So as we are giving in what form, students? So this is what parallel in. We are giving PI, right? All bits are in parallel form. This is PI. Parallel in. What are the outputs? It is also parallel out. So this is called PIPO form. Parallel in and parallel out. We have taken. If it's the same data, you want to design for SISO, that is serial in and serial out. How do we get it? For to getting that particular thing, that also we can design by using any types of flip-flops. Let us see how do we design by using serial in and serial out. Means inputs we can give serially and we can get the output in serial form. So students, so next way we can design this D flip-flop for 4 registers by using serial in and serial out. How do we get that? We can connect 4 D flip-flop in serial wise like this, right? So one we can give the common input, I0, I1 become now common for D. This is in this output of that will be Q, will be passed to the input of the next one, and the output of next would be passed to the input of next one, output of the next is passed to the input of the next one, and the output here is SO, that is serial out. What input we are giving? The input giving is I. This is what? Serial in. So this is in serial form, we are giving serial input. So we are getting the output in serial form, that is serial out, right? So we have to give a common clock for all the kind of flip-flops. So the clock pulse we are giving positive edge or negative edge based upon the operation. This is the common clock pulse, right? So this is the clock pulse. We are giving CLK, right? So this is also the way we can design the registers of 4-bit by using SISO, serial in and serial out. So you may know it if you don't know it, but we can have this data passage by various forms: serial in, serial out, parallel in, parallel out. Just now what you have seen, you can have serial in, parallel out, or parallel in, serial out. This is the way you can pass the data into the registers in this various form. So we have done with serial in and we can done with parallel in and parallel out. So remaining also you can do it, but only for understanding purpose this is enough. Serial in and serial out, parallel in and parallel out, passage of the datas. So students, next we will take how do we design the ripple counter. One example I'll take by BCD ripple counter. So we are having two, they are different types of counters. One is the synchronous, another is the ripple counter. So basically what is synchronous means clock pulse is given commonly and the inputs whatever we just seen by using D flip-flop 4-bit register, that is synchronous one. Then what is BCD ripple counter? So if I want to design this BCD ripple counter, I'll take just now the example of what we have taken. We have taken 4 types of what? Types of flip-flops we have considered, right? So I'll draw it. First flip-flop, another one. Likewise we will take 4 different types of flip-flop, right? What we have given? We have given inputs to it. What are the outputs we wrote? A0, then A1, A2 and A3. So inputs are what? For the first thing, if it is designed by using D flip-flop, I'll write D for all. Like this I wrote it D for all the inputs. Next thing, I need to give a clock pulse. I'll give one common clock pulse, or I can say that whatever the inputs I'm giving, this D I'm giving as logic 1 or higher logic. So, or I'm giving the supply. Supply is considered to be here logic 1. Next thing, to design this kind of flip-flops, main important thing would be how do we get that flip-flop by considering the ripples. Ripples means it is asynchronous. The input of the next will be passed to the output of the next flip-flop. So that way I need to design the ripples for that particular flip-flop. So for doing these things, what I did, I gave a logic 1 to all the inputs, right? Next we left out is reset bit, and we left out with the output of the next is passed to the input of the next clock pulse. So meaning is that what I did, I passed all the inputs here. What is left out now? Clock pulse. So clock pulse I'm giving like this. This is your clock pulse. But for the next clock pulse, this is considered taken from the output of the previous one. Previous output of the first flip-flop is taken to the clock of the next. So this is your next clock, right? How we get this clock then? This is taken from the output of the next. Okay. Likewise, for this clock, how do we get it? It is taken from the output of the next would be taken from the input of the clock pulse. This is your output now. What is left out? Reset. Reset, reset, reset and reset. This we will take and we will give one common reset. So for this, separately I'll give reset from here. Don't be confused with the lines. Lines needs to be drawn properly. Connections would be just explained with the proper doubt. Okay. So this is a reset one, and this also having a reset. Okay. So this I'll mention here. This is what? Reset or clear. Right. So this is the way the ripple BCD. BCD means what is a BCD code? BCD code should have from 0 to 9, right? So the bits are from 0 to 9. If you do have this kind of bits, then it's considered to be the BCD code, right? So this is the way we can design the ripple counter. So ripple counters is having a slight difference when compared to the previous kind of counters what we are going to see, and what we have seen just 4-bit register. So here the clock pulse will give in the previous condition common, and the inputs also we have given separately in parallel out form. But over here the whatever the inputs is there we are giving as logic 1, or that supply is needed for that. So that's the reason we gave a supply to it, and the outputs, to get the outputs, the first A0 is becoming the clock for the next types of flip-flop, and A1 is becoming the next of it, A2 is becoming next of it. This is your A3. A3 is the actual output for these ripples, right? So now I want to write the state diagram for it. How do I get the state diagram? 0 to 9 I had, right? I write state 1, that is bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, bit 8, bit 9, and then again it will come back to this position. So what is the first combination for BCD? 0 0 0 0, right? Next combination 0 0 0 1. Next is 0 0 1 0, 0 0 1 1 3. Now 4 will be 0 1 0 0 5, 0 1 0 1 6, 0 1 1 0 7, 0 1 1 1 8, 1 0 0 0, 9 is 1 0 0 1, right? You can draw properly one complete circle. You can make it like this. Like this, all will come in this way. Because I don't have a space, I draw like this. This is what? State diagram. We are just counting the ripples for BCD codes. So this is the way the circuit diagram and explain this BCD codes. Equation, for D flip-flop by using characteristic table and excitation table. Excitation table is left out, that I'll explain in the next class. But the diagram you see, and how do we design the ripple counter? This is an important question. They can ask you to design by using D flip-flop, or by using T flip-flop, or by using JK flip-flop. Okay, so ripples counters, state diagram, and the circuitry representation of BCD codes. So just make a note of it. By using D I mentioned, this is by using TU, right? Though it is not a D, it's a toggle. This designing what I did, it's for T flip-flop. Okay, make just change of it. D flip-flop also, it's quietly the same, but the thing is slight difference is there. What was that difference? We will see when we come to design it. It's toggle, T flip-flop. In the question, this question is for T. T flip-flop design a ripple counter. Okay, T, you modified it and write it down. The sequence and its representation of BCD code. That's it for today's class. So in today's class we have discussed about registers, counters, state diagram, and in registers we have seen 4-bit data registers. So how this 4-bit data register is going to be work, that also we have seen in serial form, in parallel form, both the things we covered it, and even the BCD counter we have seen. So what we have seen from starting, students, we have seen this first, right? This is our first topic for discussion. What we have seen in that, we have seen how do we get the 4-bit data registers. After that, what we have seen the serial input. How do we get the serial in, serial out form for this same 4-bit data registers. After that, we have come to our main topic of discussion is counter. In that we have taken T flip-flops. By mistakenly I've just mentioned over the D. It's not D, it's a toggle, T flip-flop. Okay, so we have seen the T flip-flops, its circuitry representation, and the state diagram. Since BCD means it should count from 0 to 9. So that means it required 4 bits. That's what for every state. For every state I just mentioned 4 bits. Thank you.